So proceeding further, we come to the chemical properties of silyl enol ethers. Now in the first small box, you can see the structure of silyl enol ether. Box number 1 shows Mukayama-Aldol addition. This addition reaction is an organic reaction, and the aldol reaction is between the silyl enol ether, that is our compound of study, and an aldehyde. Now the reaction was discovered by the scientist on whose name is the reaction named. His reactants allowed the crossed aldol reaction between aldehyde and a ketone or a different aldehyde without cross condensation of the aldehyde. So this reaction is very widely used, extensively used in organic synthesis for various purposes. Then moving further, in box number 2, we see a set of 3 reactions which take place in the presence of TiCl4 and ZnCl2, all giving more or less the same type of product, where a beta pi cleavage takes place and the position adjacent to the silicon addition position gets occupied by the reactant, which is in addition to the silyl enol ether. Next, in box number 3, we see alkylation and dimerization reaction. Dimerization reaction, if it is taking place with the straight chain ether, then it has to take place in the presence of silver oxide. However, alkylation reaction again brings about pi cleavage, and the alkyl group attaches at the same position where methyl group is attached, along with the removal of trimethyl silyl halide. Dimerization reaction gives a dimer where R is the alkyl group, that is the straight chain compound. If you can see in box number 2, dimer is also obtained in the third reaction, where in the presence of TiCl4, where it is the phenyl group. So this is the difference between if the adjacent group is alkyl or phenyl. If it is phenyl, then TiCl4 is to be used, whereas if it is alkyl, then Ag2O is to be used. So these were some of the chemical properties of silyl enol ethers.